Opening comment. Please. Get started from where we left yesterday. This discussion we can have later. Coming back to antennas. So it was great that you had a lot of questions on this and why does primary beam matter so much. So just a quick recap. When we derived the actual radiation pattern of a dipole antenna, what we saw that its radiation pattern had an angular distribution. And from the Poynting vector, we saw that it basically depended on two things. L by lambda squared, which is the length to the wavelength at which you are planning to operate, times sin square theta. Theta being the angle perpendicular to the axis of the dipole. So ideally we would want, precisely because of these effects, to not have any lambda dependence on your primary pattern. So as long as your field of view remains the same, you will get, or you will faithfully reproduce what the intrinsic spectrum is. But that's not the case when you have dependence like this. So the reason is, why do we not do that all the time, right? Why do we not design antennas that are frequency independent? And the answer to that is, it's not possible. So I want to give you a quick demo before we move forward about how we actually go about designing antennas in real life. I think there's some bit of a noise in this. Can you hear me all right without this?
No, it's fine.
It's fine? Okay. So then I can just continue like this. There's some noise.
You can turn it off.
Is it? Okay. Yeah. So I wanted to give you a demo exactly on the same dipole antenna that we had discussed yesterday, right? So just a quick recap. These dipole antennas are essentially two arms here, right? And you are basically injecting something to look at the radiated power pattern. And we also said that it's a reciprocity theorem. So the properties as a transmitter will remain the same as the property of the antennas as a receiver. So there is a very nice notebook by Mathematica on this. It's essentially analytically computing what your radiation pattern should be for different values of L by lambda. So how if this is changing, and of course while deriving the electric field, if you remember, the very first assumption we had made was because your length is very small compared to lambda, your electric fields will add in phase across the length of the dipole. That's not going to be the same if you have length that is comparable, right? So all that computation has gone in here, basically to show how the beam pattern changes once you increase L by lambda. So when the L by lambda is small, we enter a regime called electrically small dipole antenna or electrically small antenna. So we start off with L by lambda, which is 0.1, right? So this is the least you can go in some way. So what you see here is a very toroidal pattern. This is again very similar to Larmor radiation field, as you may have studied in physics. So because the mechanism remains the same, right? The motion of electrons in the antenna is the same as motion of electrons in your magnetic fields in the galaxy, right? There's no difference, both are Larmor radiations. So this is basically the way to look at it is the beam is perpendicular to the dipole. So your dipoles are like this, right? So the toroid is perpendicular axis to that. And so along the elevation axis, so from horizon to zenith, it follows this pattern of 8, right? So its maximum goes to null, but along the azimuth, it is symmetric. So it traces a circle here. But then, what happens when you increase this L by lambda? So let's make L by lambda as 1.1. It flattens. So it's still well behaved, and I'll tell you why this is well behaved because we'll look some rogue beams. What you can see is basically its beam width has reduced, it's flattened, and that's simply because this width actually is inversely proportional to your length scale of telescopes. We'll get there soon. But it still continues to trace an azimuthal symmetrics along the phi axis and a shape of 8 along the elevation axis. Now you start seeing the problems. So what happens is when you make it electrically very large, so we are talking about L by lambda 4, which means if your wavelength is 3 meters, you're designing antennas which is 4 times that. And with this you can see that azimuthal symmetry remains because there is no variation along that axis, but your elevation response has a lot of what we call as lobes. Till now what you are looking was just one single main lobe, right? But then as you increase your length, essentially what happens is when you sum the electric fields, now you have a huge phase along your dipole axis because your length is large. So you go multiple cycles of 2 pi. So because of this constructive and destructive interferences along the length, you have all of these kinds of structures. Basically some kind of an interference pattern. Now this is very, very abysmal for any kind of 21 centimeter experiment. You would not want a beam that looks like this, especially so for global 21 centimeter experiments. And it just keeps on getting worse, right? And another point to note that is its frequency dependent, right? So you can imagine my L is constant, I am just keeping my lambda changing, right? So at 40 megahertz, your lambda is around 6 meters. At 200 megahertz, it's around 1.5 so. So just by changing lambda, you are varying this ratio. So in some way, this also you also had a visit to the lab where you saw PON antenna. They are electromagnetically very hard to model. So the moment you go to any kind of a profile structure, analytically solving equations to derive your electric field becomes almost impossible. So then you have to resort to some numerical methods or some simulation methods. So how we do that in our real life? We use a lot of what we call as EM softwares. So this is one of the EM softwares. Maybe some of you have used this before. This is horn antenna, so exactly what you saw there. And this was one of the first antennas in radio astronomy. I don't know, do you know which antenna was used for Benzia's and Wilson CMB experiment? Horn, yes, I gave it away. Okay. Yeah, so it was horn antenna because horn antennas are traditionally very good for communication. They have great directivity. So again, antennas have applications at several places. Astronomy is just one of them. And you will have very different specifications of what is acceptable depending on what you're looking for. So for communications, for example, you would want antennas which are highly directional. Right? They don't really worry much about frequency dependence as much as we do. So these horn antennas are great, and that's what they were trying to do. They wanted to set up a cross-Atlantic communication. So this is horn antenna. So what you do is, if you have done a CAD design before, you basically build a CAD model of your design. You have lots of free parameters here. So opening angle, the dimensions themselves, the axis of symmetry in your surface, all of that. And then you mesh it. So the points that you are seeing here are basically the meshed points here. And you can look at different views. So you can see it's very finely meshed. And this meshing is not very different from what you have studied for the 21 centimeter modeling. So you basically solve your electric field at each of these mesh. And there are various ways to do this. Essentially, all you are doing is solving Maxwell equations and producing the electric field distribution on the surface. And your antenna properties are all derived from that. And we'll touch upon that, but this is just a practical demonstration. So what are the quantities of interest here? So once you have a design, you essentially run a simulation. That simulation gives you electric field patterns. And there are things that you can physically translate to what you will measure, right? So let me show you those. So the very first thing that you would want to see is the beam pattern. So for this, we ran this simulation. This antenna was designed at lambda equals 3 meters, 100 megahertz. And right now, I don't know which frequency is this, 108 megahertz. So you can see how its radiation pattern looks like. It's not a very simple radiation pattern by any means. And this is log scale, so that's something to keep in mind. Now, what you can do is you can also look at other frequencies, how it changes. So when we go to very low frequency, this is 40 megahertz. In general, what you'll see, your primary beam gets wider with lot of, in this case, also side lobes. So there is a main lobe, but there are also these side lobe features. And then these get very accentuated when you go to higher frequencies. So suppose I go to 200 megahertz. So the beam gets narrower, but now you can see more features. Right? So this is one aspect that you can very clearly see in these simulations. But you don't stop there. I mean, yeah. The gain, the color is basically the gain of the antenna in different directions. That is the log scale. I'll show you the 1D plot. It's clearer there. So, but you don't stop here, right? I mean, visually, yes, sure. You can look at it and say, okay, this might be okay. But eventually, you want to translate everything to how it affects your measure, observable, which is your antenna temperature, right? So you want to take this beam out, plug into your measurement equation, which convolves your beam with the foreground sky. Foreground sky we have discussed in plenty. And try to see how these features get imprinted in your antenna temperature. And based on that, you decide whether this is acceptable or not. So just to show you a few 1D plots here. So basically what I'm showing now is you cut a slice along the phi axis. So you're looking at how it's changing along the elevation. And that is this plot. And you can do this for different frequencies. So for example, right now I'm plotting 100. You can go till 200. And you can see the higher you go, the more structures you start getting in your primary beam. And maybe the other one I can go to 40 just to contrast it. So it is 40. So this is just a 1D slice. And here again, what we are plotting is basically the gain of the antenna. I'll come to what that is, but it's a representative of your angular distribution of your field of view. Like how your when you transmit something from here, how it's going to be distributed. Right? The other quantity, and I'll come to that in my slides, is the impedance of the antenna. That also matters a lot. Until now, we have been very conveniently ignoring this. But when you have a electromagnetic wave incident on a surface, you might have studied this electromagnetics. not everything is transmitted, right? So you have all the three processes, which is transmission, absorption, and reflection. And this ratio is decided by the impedance of the antenna, how well it is matched to rest of the systems. And these antennas or antennas in general are not matched. So whenever there is an incidence, a part of it will always be reflected back and rest of it will be transmitted. There is very little loss because most of the antennas are metallic, right? So the losses are very small. So you might want to look at how this transmission coefficient changes with frequency. It's not dependent on your angle, right? It only depends once you have a power at the antenna, how much of it is transmitted into the system. And that is direction independent. So in antenna engineering terms, we call that return loss. It's a very tricky statement, but I'll just write what in this plot. So what this is showing is what is called as S11 in dB units. Not a very helpful unit. You can convert this to linear. That we will call gamma. So your antenna temperature is nothing but 1 minus gamma squared times whatever is coming at your sky. Let's call it T. So T prime is already being weighted. So after your primary beam convolution, you get this. But not when you actually look at the data on your computer, you will not receive this, you will receive. So this modulation term is decided by how well you are matched. So we call this return loss, we call this S11, there are different terms, but they mean the same thing. And again, it's very clear. So if there are any spectral features in this measurement, in this gamma, your sky signal is going to be multiplied by that, right? You can see your reflection coefficient. Here, the way to interpret it is the more low it is, so you can see it's all negative, minus 50, minus 40, minus 10. The more negative it is, when you convert it into linear, you'll go to 0.001 order of those numbers, which means your matching is very good. And most of your TA is actually getting coupled into your system. So for a typical antenna design, this is very good. The problem arises because of these features. So there is an absorption at 100 megahertz. You don't want it. Because if you miscalibrate this, you might end up producing absorption features in your data that is not related to your cosmological signal, but your antenna itself. So spectral features in your S11 directly translate to spectral features in your observations. And of course, we can try correcting for it. The question is to what accuracy you need to do that. Right? So these are the two parameters primarily that we want to focus on when we design telescopes. So you want to know your radiation pattern, you want to know your impedance. And based on this, you basically iterate and come up with a design which you think is acceptable for your science. Any questions till now? Yes. You mean this one or it matters? Even when you are averaging, yes, it will reduce the impact. But we have seen for very specific classes of radiation patterns, it introduces something which is persistent. Yeah, but that's good. Averaging helps us a bit, but not all the way.
We don't want to
No, even the diffuse emission, it matters.
know this pattern very well. We can always get
So not subtract, yeah, you can divide because this is a multiplicative effect. Yes, that's a great question. We can always try correcting, and we actually, as a matter of fact, all of us do that correction. The question is how well you have to correct it for. So let's do that very simple exercise here. I want to look at error on my data. Okay. Assume TA is constant. So what is the acceptable error in the measurement of gamma? So that the measurement in data is around 1 millimeter. So the TA typically for these frequencies you can assume to be 1000 Kelvin. So order of magnitude, the accuracy to which you have to measure this is of the order of 10 raised to minus 6. Our current instruments, the ones which are efficient, go up till 10 raised to minus 3. So either you design your own measurement such that it's accurate, and we have done that too. But more importantly, there is a lot of chance of error when you are trying to make such a precision measurement of your responses. So even a very small miscalibration here, right? All you need is 10 raised to 6 minus 6 to something to 10 raised to minus 5. You will produce signals at 10 millikelvin, 100 millikelvin. And that is the dangerous territory. So it's not that we cannot live with ripples like this. We can, if you are able to calibrate it to that accuracy. Any other questions? Yes. Yes. Yeah, I'm getting it. Yes. So polarization is also important aspect. Your impedance is agnostic to what polarized component it is, because it's interaction of electric field with the surface. So that gets imprinted onto your beam pattern. So typically for cosmological signal, if it is completely unpolarized, which it is, if you just have one antenna, you will receive half the power, equally distributed in X and Y. Okay. Any other questions? Fine. So let's move ahead now. So this was just a small demo. I'll close this. So in rest of my talk, I'll try to do two things. And great that you brought up this question about measurements. So we will see, first of all, mathematically. I'll again get back to the question, what are we measuring? Because that's a question to ask. I'll derive some of the quantities. And finally, we will look at currently how different telescopes are trying to measure this. So one thing that I think I already talked about it, this is basically the gain of the antenna, which is, you just saw a bunch of beam patterns. And you could see some of them are wide, some of them were narrow. How do you quantify this? So this is quantity in terms of gain. So essentially, when you inject some power into the antenna, it has radiated. Of course, we are assuming lossless antenna. Now, in what pattern it radiates is the question, but the total power has to be the same. And that's why this relation holds, which is G is basically the gain. And how it is defined is in a specific direction on the sky. Whatever antenna you have, say horn antenna, how much power it radiates compared to an isotropic. An isotropic antenna is just a hypothetical antenna that radiates uniformly in all directions. Never existed. But the question is, in a given direction, how much extra you are radiating compared with that isotropic antenna. So if you have a very high gain antenna, which is what people in communication systems desire, what you are seeing is that a lot of your power is transmitted in a very specific direction on the sky. Right? The rest of the places it doesn't really go compared to an isotropic antenna. So basically, higher the gain value, lower is your beam, like lower is the width of your beam, and it's very directional. On the other hand, if your beam is wide, your gain will be very low. And in other way to quantify this is by solid angle. Basically, the integral of your beam over theta and phi, and they are related. The integral will always be 4 pi because it eventually has to be distributed. So it's just a question of the interplay between high gain. So the higher the gain, lower will be your beam width. So the integral will always be 4 pi. Because again, conservation of energy. So that was about gain. But what I want to tell is something which is very important. Basically leads to the measurement equation that we have been using till now, which is when you measure antenna temperature, what is it are you measuring? Especially when you look at a diffuse sky and when you look at compact object. These are very important distinctions. Okay. Any questions? We'll get started with this specific derivation. So what you are seeing here is a dipole and our same old dipole that we just saw. You have connected the output of dipole to a resistor. Resistor is basically lossy, so it's dissipating heat. Two compartments have this slot. What this slot is doing is basically limiting the frequencies of radiation that can be transferred between the two. But important part is these are thermodynamic equilibrium systems, which means the temperature there and temperature on the resistor side are the same. This becomes very important. So in some way, you can't heat up the resistor, because once you heat the temperature in one side, it becomes higher and the other side becomes cooler. So, but they are in equilibrium. So resistor is dissipating the heat and antenna is picking it up. So in some way, it's an equilibrium system. That's our setup. The reason why we have this weird setup is to see what antenna will actually sense. What is the power that antenna will measure when it is enclosed in this thermal bath with a resistor. And this also ties up with the definition of what is antenna temperature. That's something you have covered in interferometric techniques, the definition of antenna temperature. Okay. Does anyone know? Because that's what we measure with telescopes, right? Whether it is interferometer or global experiment. All we measure is antenna temperature. So, and we measure antenna temperatures of thousands Kelvin, even more. What does it physically represent?
I have a resistor. That is a transmitting power, and that transmitting the same power. What means
Precise. No, that is precisely what it is, and that's why this plot gains a lot of importance, because antenna temperatures are not physical temperatures. That is something we should establish. When you are observing with your telescope, you will measure temperatures of 1000 Kelvin, 10,000 Kelvin, even a million Kelvin, depending on what you are looking at. RFI can go up till billion of Kelvin, the interference. But it's not that thermally they are at those temperatures. Impossible. So what you are doing is, it's basically some kind of a radiance approximation, which is you are asking, okay, I receive a power which is so much in specific intensity units. How much should I heat a resistor? Because basically resistor also has a power, and that power is given by something called Johnson noise, right? That the total power that you will see in a resistor. So what you can do is you can connect the terminals of your resistor to an oscilloscope and measure how much is the noise power. You will see that power in that resistor only depends on the temperature. This is the physical temperature of the resistor. Mind it, it does not depend on the value of the resistor. It only depends on the temperature and at what frequency range. At what frequency range you are measuring that power. That's it. Bandwidth. KTP, and we'll be using this extensively. So the question is, when you measure something on the sky, what temperature should you heat up that resistor to get the same power? So that is the definition of antenna temperature. So it's not a physical temperature at all. It is an equivalence drawn from a resistor. And that's mostly because I think initial radio astronomers or electrical engineers. So when you say kelvins, this is what we mean. Now, sorry, any question? Yeah.
You're saying that effective brightness of the source is some Kelvin.
Yeah.
That is, in that I am relating the specific intensity to the brightness to the dialysis circuit.
That is for the brightness temperature, not for antenna.
Antenna temperature is what I am getting out of the antenna.
Yeah. After the convolution. So yes, on the sky when I say galaxies 1000, what I mean is religions approximation. This is also sort of that, but through a resistor.
That is multiplied with the antenna pattern and
we'll derive that exactly. Yeah, that's the whole. So you'll see the equivalence of the two, right? Yeah. Any other questions? No, so I'm coming exactly to that because I think it's a very fundamental part of radio astronomy. So you have studied specific intensity. What's the unit of specific? So someone said watt. Second comes in what? And as you know, this is a very telescope independent quantity because you're normally by the solid angle. What you measure is its specific intensity. What is the unit of flux?
Just stated in the
Okay. Let's call this I nu. Let's have SU. So your flux is something which is integrated over the solid atom. So this is a very telescope dependent quantity. So when you measure in interferometers Jansky is this flux density. It's actually called flux density. And flux density is integrated over solid angle. So different telescopes will probably measure different things. What you want is Jansky per beam. Basically per beam is per second. But you get the sense. Specific intensity is independent, that is intrinsic property of the source. Your flux density is not. Just a distinction. And the reason that I bring it up is because my derivation depends on it. So, you know how much power this resistor is transmitting per unit frequency. We just thought resistor over the entire band will have this one. We are looking at per unit frequency here. So it will just be kT. And they are at the same temperature. So the power that is measured by the resistor is kT. And the same power is sensed by the antenna. But what you can do is you can write the power which is sensed by antenna in terms of these units. And that is nothing but your flux. So this will depend on the specific intensity, and this is a Planckian because this is thermodynamically equilibrium state. Now, if I want to measure power, I have to multiply this specific intensity with area and the solid angle to get basically how much power is being transmitted, which is what kT is.
Can you please explain that?
This one. So I am equating the power in the resistor to the power measured by the antenna.
Like, antenna is receiving power from outside.
No, from resistor. This is a closed system. So on one side, I am listing what is the power from the resistor, which is a kT. This comes from Johnson noise. On the right side, I am going to write what antenna will receive. It should be equal to kT because they are in equilibrium.
Then through the wire.
Yes.
There's no radiation.
So the specific intensity is B nu. This is Planckian. And you multiply it with some area, right? Because you have to convert this to power. You multiply it with some area. That area is what we call as effective area of antennas. What else do you need to multiply? To get the power. So we have specific intensity multiplied by area. What is the next thing? Per frequency. So this radius. Yes. There is one more factor, which is what I think Akash had asked. Polarization comes into it. Your dipole is linearly polarized. You will not receive the full power. You will only receive half the power. So this is the power that your resistor is transmitting. This is the power that your antenna is receiving. So I will not do the full math in respect of time, but essentially this is a black body path. So you exactly know what your BU is. When you do basically plug in this BU, what you will see is a very nice result. Tell you why this is so important. So I'll derive two results. This is first. This is basically telling me what is my effective area. And this is simply coming from here because we wanted to convert intensity into power. The nice thing that you see here, effective area of dipole, or for that matter any antenna, only depends on the lambda. It's not the geometric area at all. It might be related, but it's not really the geometric area. You can't just take length and breadth of the dipole and say that's my antenna area effectively. Because what you're getting is this relation. So I basically took some average value and made d phi to be 4 pi. So what it says for this
relation.
Yes. Yes. But it's a lambda dependent answer. That's what I wanted to focus. It's the area, the effective area of an antenna. As you know, area is what determines the sensitivity. When you're designing a system, you want to look at a source with some flux. You also want to know what frequency you're looking at, because the same antenna can have different areas at different frequencies. And that's why you see, for example, MWA, these are dipoles. And they are very discrete systems. They are what we call as elemental antennas. On the other hand, when you look at SK mid, these are dishes. Why do you think at higher frequency we go for dishes, and low frequencies we can live with these small antennas like MWA, low power? All of these are elemental antennas. And the reason lies here. Eventually, all of us want high collecting area or area of antenna because we want nice sensitivity from our telescope. At low frequencies, high data values, you anyway get very high effective area just because you are operating at long range. So even if you make antennas dimensionally very small, like MWA as you have seen, doesn't matter. You can still, you will have a very high collecting area. Very counterintuitive because geometrically it's the same system. But this will not hold when you go to higher frequency. That's why beyond say a few hundreds of megahertz, if you are designing a telescope which is larger, you have to go for dishes. Right? You can't be living with these elemental antennas. You will simply not have enough collecting area to get the sensitivity that you want.
Basically, area of the antenna is given because power pattern changes.
It's not really power pattern. It's basically that electromagnetic radiation, when it has a long wavelength, if your dimensions are small, it almost sees it as a solid surface. Like GMRT is a mesh, right? The reason for that is the same. At those frequencies, that mesh is not visible. It acts like a solid dish. It's in some ways averaging out over that range. But if you want to operate GMRT at 100 gigahertz, impossible. There, the mesh things comes into. So it depends on the kind of gaps you have. What's the lambda? Does it see it as a single body or does it see it as discrete? So this was one very important corollary that we should understand, and this is a very applicable thing you will see around you in all the telescopes. Any questions? Okay, if not, we'll simply go to the next part of this. And in the last few minutes, I hope I have last few minutes, I'll basically show you some of the slides of how different antennas are trying to measure this topic. Okay. So the next thing that we want to do is see how antenna measures discrete sources and how does it measure diffuse sources. And this is in context with a single antenna. So we keep it as is because I think our other derivation is related. One thing which I have written there but probably ignored talking about is this effective area and the gain that we discussed are related. And the simple reason why this is reciprocity. We talk about collecting area when we think of antenna as a receiver, right? So it's receiving some power from resistor. But when we talk about antenna as a transmitter, the gain becomes important. So in some way, they are actually almost the same quantity. They are just factors of 4 pi here and there. But overall, they are not different at all. Though again, dimensionally, one is radiation pattern, one is a collecting area, but they are almost the same quantities in radio astronomy. Okay, so we'll go to this part and then we'll simply look at some of the telescopes. So I'll again start from the same equation, this one. That is the temperature of that resistor we saw is related to the effective collecting area of the antenna. And what you can do is you can make this B new here. So we are basically looking at again the images. You will find the following. And this TB is nothing but the same T. So this is the brightness temperature of the source. What we did, and I'm basically skipping a bunch of steps here, is we took some source on the sky that had a brightness temperature of TB, plugged this B new here to see what the power antenna receives. And that's what we get. Now, as I said, collecting area AE and the gain are related to each other, as we saw in the previous diagram. One is basically a transmitter and another is a receiver. So we can interchange between the two. And the strict relation between the two is this. I'll not be able to derive it here. Effective area and gain are roughly the same quantities. So when you plug this in, you basically get the expression that we have been using since lecture 1, which is, here, write it here, P of A and like this is all coming from a resistor in a box. So the antenna temperature that you measure for a source that has a brightness of TB, you are doing this. So there is a radiation pattern involved, which is related to your collecting area, actual brightness temperature of the source, average over some solid angle. And this is basically integrated over entire theta and pi. That is what gives you antenna temperature. So this is what we have been using all along. Now what happens when the source is extended? So suppose I am looking at the center of the galaxy. I think we all did in the tutorial. In that case, you can assume that TV doesn't have much of a brightness variation because it's filling up your entire primary beam. You take it out. And what is this? 4 pi. This is the conservation of energy. Your gain times the solid angle has to be 4 pi because that's the power you are injecting. So this was, I think, your question. How is brightness temperature and antenna temperature related? For diffuse sources or extended sources which are filling up your beam, they are exactly the same. When you look at a galaxy, you measure 1000 Kelvin. This 1000. That is basically the brightness temperature of the source. And this simply comes because this integrates. So for all the global experiments, all we are trying to measure is the diffuse field, right? So we are looking at the 21 centimeter cubes that we have simulated, and they also span a lot of length scales. Same happens for the foregrounds. So what you measure as antenna temperature is nothing but the brightness temperature. They are exactly the same quantities. You might just okay. But what happens when you measure diffuse? And this is where the primary difference between the global experiments and interferometer lies. So what happens is the following. In interferometers, you actually are very sensitive to compact sources. This is what you have seen in other classes. But in this case, what happens is this. Yes. So we'll use the same equation, which is the antenna temperature. For a compact source, you can basically discretize this. You're only looking at a very small solid angle. That is 1 by 4 pi at some solid angle. And this basically is the solid angle of the source. call it omega S. And we saw that the gain and the solid angle of the antenna are related. Twice. So what you measure in case of a compact source is this. If you don't want to remember other things, fine, just remember these two. Which is, what does antenna measure when you have a diffuse structure, and what does it measure when you have a compact source? So in case of diffuse structures, you are measuring the real brightness on the sky. But when you have compact structures, your intrinsic brightness of the source is diluted by this factor. Because your compact source solid angle will always be less than solid angle of the antenna. We just saw the beams are pretty wide. So solid angle of the antenna will be large. So this quantity will always be less than 1, which is not the case for interferometers. So that's why for compact objects, they don't really matter so much for us, because even if they're intrinsically bright, what we measure is not at all, because they're diluted. And this factor is huge. It depends on your antenna for sure, but this factor is very appreciably large. So even for the brightest of the sources like Sigma 6, Cassiopeia, these are very bright sources, you won't really find them in your data much because of this dilution. So in some way it's good for us for 21 centimeter.
So for 1 minute.
Yeah. So what you really measure is the ratio of it. That's basically the take-home message. Any questions on this? Oh, that's because you're only looking at a compact object. You're not looking at the underlying diffuse emission. So you, in some way, your TB is only at that omega S. Other places it's 0. It's a delta function. Well, it's a Gaussian, I would say, not a delta. Because there is some solid angle of the source. It's not infinite. Any other questions? Okay. I promise this was the last derivation. And we'll simply do, so basically now you're familiar. What's the primary beam pattern? What is the impedance of the antenna? And the third thing, what does the antenna measure? So these are the 3 primary things that you need to know when you look at a radio telescope. Right? So the question is, how we measure these quantities when we come to global signals. Now, one thing which I'll skip and you can study it yourself is when you want to measure, for example, we have GMRT, you want to measure the primary field pattern of this antenna, like one dish. Any ideas how to do that? Clearly, you know why we want to do this, but how do we want to do this? Using a drone. Great. Anything else? Has it been done? Drone measurements. Okay. Right. Yeah. So that's one way. What else? Sun. Okay. Some bright source on the sky. Yeah. Sun, you said. Why sun of all the sources?
No, because it's very bright.
Okay, it's very bright. It's also variable. Variable, yeah.
This telescope is trying to.
I was part of it.
Yeah.
That's why I was curious how you know. In Chime Telescope, we did that. Yeah, and it worked out very well because that was solar minima. We did it in 1819. So the solar variability was really low. Now we can't do that. It's becoming active. Anyway, so yeah, so there are ways to measure the beam. The question lies how and to what accuracy. One thing one has to keep in mind is when making any of these measurements, you can't be arbitrarily close to the antenna because your very presence will affect and completely change the radiation pattern. And that's simply because you are in what we call as near field. So you are also a dielectric electromagnetically. So when you are near, you are also part of the antenna. And therefore, in order to take a measurement, you can't be very close. And the way we formally derive it is basically at what distance, if you again assume this to be a transmitter, you have spherical wavefronts, at what distance they start becoming parallel. That's the place where you want to do these measurements. So initially I had in mind to derive that, I won't, but what I want to drive away is those far field distances are very large. So if you want to really do a beam pattern measurement, of course, you have to be sufficiently far. That sufficiently far is far field, and that far field for these kinds of telescopes are very high. So if you want to get a sense how far you have to be, it's proportional to 2d square by lambda. This is the diameter of the dish, and lambda is the wavelength at which you're operating. So try doing that for GMRT. I have given the diameter. You can choose wavelength of your choice, and tell me how far you have to be in order to do these measurements. You'll appreciate the numbers. You can also do this for another very big telescope called Singh. This 100-meter diameter, and it is operating all the way to millimeter.
Or 150 kilometers.
2 kilometers. What lambdas you have taken?
2.
Of the order of kilometers. Yeah. So you have to be a few kilometers away when you want to do these measurements. Otherwise, your own equipment will become part of the antenna. Right? So one has to, and if you calculate the same thing for this, you will find thousands of kilometers. So one very practical consideration is, while measuring these, you have to be in the far field. Just wanted to drive that message across. Your drone can actually fly high. So in principle, it's possible. Actually, my next slide is exactly on those. Beams? I'm not aware. Drones, I know. Balloons, not so much. Basically, what you need to know is you want to inject power at different parts of your beam and see how much you're receiving. Balloon stability and drift rate might be very different. Drone is more controllable. Yeah, and that brings me to the last topic of today, which is you've seen simulation, so that part is done. Characterization. Once you've designed the antenna, how do you characterize it? So there is a very nice paper. How many of you know this experiment? It's a very nice one actually, because in radio astronomy we always fight whether cylinders are better or dishes are better. So you see UT radio telescope, how many of you have seen that? That's one? You've not been to radio telescope? I think in next school we should hold it at UT. Yeah. Okay. UT radio telescope is one of the most elegant ones, I must say. It's cylindrical, as you may have seen in the pictures. I hope you get to see this in real life. And then you have GMRT, which is dishes. Can't go into the details of why we chose two very different things. They have combined them. So you have cylinders right here, dishes just next to that. This is called biannual. This is in China. And this is, of course, science goal is not really EOR. Science goal is what we call as baryon acoustic oscillation measurement. We'll not get into the details. But they've done a very nice exercise of characterizing these. It's operational. Yeah. So they flew exactly the manned aerial vehicle, the drone, over the dish. It's a nice picture. And you literally just radiate as you go along the path of the antenna. And what you want to do is you want to measure that, how much power you are receiving when the drone is flying along this. And of course, there are projection effects that you can later on correct for. This all is taken from this paper. So what you get, you raw data when you do this, you are radiating along this flight path, you get something like this. So this is your received power as the drone flies from one side of the antenna to another side of the antenna. You can ignore these parts. These are when the drone was actually going to a height. So the real measurements probably start from here. And this is just raw. This has not been corrected for any kind of a projection effect, right? When you correct for those, you get something like this. And this is what the beam pattern is, right? So the x-axis is basically your what we call as hour angle, so zenith, and then both sides of zenith. And the amplitude is basically the gain of the antenna, what we have discussed in very detail here. Given that it's a dish, you can see the kind of lobes that you have. We also saw this in the simulation when we were changing lambda by d. You will have these kinds of structures because they're electrically large antennas, as you can see from. These are very, very large compared to the wavelength. Here the wavelengths are tens of centimeters, and clearly these antennas are much larger, so you will have side lobes. And someone said we can also use sky sources. Samit, you did. So they also did that. So the red line is using Cassiopeia, which is one of the supernova remnants in our galaxy, very well characterized. And you can see there is an appreciable measurement. Why do you think it doesn't match once it goes away from the main lobe? But it's the same frequency. You can see it's flattening, it's not really going here. Yes, your sensitivity limited, right? Because the source is not as bright as a drone signal. So this then becomes a question of accuracy. So that's why bright source, and that's why sun was very important, because sun was so bright that you can also map side lobes, which is not possible really with standard sources. But this was, I thought, was a very nice exercise. Yeah. You have to send it. So directivity of your antenna, you're using an antenna in the drone also, right? The directivity has to be very sharp. So in our jargon, the gain has to be very high. It has to focus the signal at one point. Yeah. The wider beam there is to then account for those scattering effects.
What is the error?
Great question. I don't know. The paper has not mentioned it. But I'll come to that. Yeah. I'll come to that.
We are measuring the gain from directly.
Which is this plot?
But if, so for some signal that is coming from what?
You take into effect the projection effects. Is that what you are asking? Which is, it's not really directing.
So my question is, if we fly the drone,
Yeah. Yeah.
and the signal is toward the radius of the thing.
Yeah.
So will the gain will be the same or different?
If you are directing towards the radius, being far, so suppose my flight path, instead of this, it's an arc. Is that what you're saying? Directing towards this.
Directly.
The antenna is always directing towards the angle of this. Towards the same.
Suppose my dish is this, my radiation pattern. I have a type, the drone here, it is transmitting right here. Now when it goes here, you're saying it transmits like this.
If it transmits like this, so
You will find the gain attenuated by this ratio to this ratio. So this projection effect you have to take into account even independent of the trajectory. So this is after projection effects. Yeah.
Drone also have a receiver.
No, right now drone can be only used as a transmitter. Receiver is your radio telescope. Yeah, so the raw data is basically output of your correlator.
We have to be a certain distance far away.
Yeah.
Far.
Yes.
There are so many antennas in the picture that you showed in the cylinders. Don't they affect the?
Great question. Yes, they do. So this has been done for one standalone antenna. The radiation pattern of a standalone antenna can be very different from a radiation pattern of an antenna which is within an array. That is a very active area of research. Yes. So this is instructive, but ideally the way you would want to measure it is in situ. You have to be in that embedded location and then measure it. That's the real thing. Because then it also talks to other antennas and that influences its radiation pattern. Because as you rightly said, these are all in the near field. They're not in the far field at all. And though these two things can be very different. I can show you a paper later, I can say, where these things have been compared. Okay.
Pattern that you show for this biannual, is it for the cylinder or for the
No, this can't be for the cylinder. This is for the dish.
what does it look like for a cylinder?
That they haven't measured it. I can show you for chime how it is. It's also a cylinder. It's elongated. I'll show you. So what are the limitations of this? Someone asked about error bars. So what do you think error bars are here?
Ideally, what I think is
Yeah,
this distortion.
very good observation. So what kind of, so now you know how this is measured. What do you think are the sources of error in this measurement? No, go ahead. Sure, stability. Yeah. Background which is radiating at the same frequency. Okay. Anything else? Temperature variation across. How will that? Are you saying there's a contamination coming from your dish thermal temperature too? And that can be different for different times.
I was not there.
But at radio frequencies, those things. Oh, for the physical temperature, you're saying. Okay. Well taken. So what you're saying is this raw power, it's a sum of everything, including your dish temperature. Yeah. Yeah. Great. That can explain some potential asymmetry. Sure. Great. So it has to be in the far field. Yeah. It was. Once it's in the far field, you can compute the phase loss. Great. Which again ties up with wind. Yeah. Stability of the transmission. So you've covered everything. So drone stability matters. So if there is windy condition, there is a problem. Positioning of the drone, you might think it's very stable, it's not. Multipath scattering. When drone transmits, someone asked about the directivity of the drone. If it is wide, it can also scatter off from other places and then come. And most importantly, drone is also an antenna. It's transmitting via an antenna. So in order to measure beam of your dishes, you need to know the beam of the transmitter. So it's a chicken and egg problem. You keep on doing this with an antenna. Right. But yeah, that is more controlled compared to a dish which is lying unused. But overall, yes. So these are limitations, but this is, as you started saying, drone is one of the most useful ways of characterizing these beams. Yeah, stability. Yeah. So the positioning of the drone then matters a lot. Okay. Just 1 minute. I think I'm eating up your time, but since someone mentioned about the sky sources, traditionally, people have actually not used drones, mostly lack of technology. So we ended up using these sources, and these sources are of different categories. This is all in Northern Hemisphere. So you have Cygnus A, which is really one of the best sources. So when you are using sky for characterizing your antenna, what you want is compact sources, right? And the reason is, if it is extended, its spatial extent starts to matter if it's comparable to your beam size. What we call it, it's resolving out. So that's why Cygnus A is compact. Do you know what Cygnus A is? Like, what kind of astronomical object it is? It's a galaxy. It's an AGN. You can see the lobes. You have Cassiopeia. These are the brightest actually. This is a supernova remnant in your own galaxy. But as you can see, size-wise, it's much wider. Then you have Tau A, Virgo A. These are much wider. Your scales are 1 arc minute. So for global experiments, these are all fun. They have 40 degrees beams. So you can use these also. So as they transit over your dish, just like your drone, and if you know the flux of these sources to big accuracy, again, it's a tall claim that you know this accuracy of the flux measurements of these, you can calibrate your beam. So that is another way in chime we have done that. So these are the cylindrical telescopes. This is what we did with sun, but we've also done this with point sources. So you can see at different frequencies. This I think is for Cassiopeia. A crab, I think one of these lies in the crab region. A crab is more bright in X-ray, crab pulses. But one of these sources is very close to that region. I don't remember which one. These are real pictures from low power. This is 30 megapixels.
So that's something that is also right.
Yeah. So now you're getting the hang of it. Yes. So
Sure about that
you know,
in the past.
right. So what you do is you have uncertainty. You know the errors on those measurements, and you propagate to the errors on your beam model. You can be honest that okay, given this uncertainty, and actually these sources are measured to around 1% accuracy, and they have been done by different telescopes. There is VLA, there is low power. Right? So, but yeah, 1% is not good enough for 21 centimeters. But to that accuracy, you can measure out as they transit over your telescopes, and you can try to do science with this knowledge that okay, my primary beam pattern is this. What I'm going to do with this. So this is the way forward. I think I've already eaten up 5 minutes, so I'll stop here. And in the next lecture tomorrow, I'll split it into two 30-minute sections. In 30 minutes, I'll talk about radiometers because this was antenna is one component. There are other things. And in next 30 minutes, it will be just a presentation because I also want to give you an overview of where we are at this stage when it comes to global 21 centimeter. What kind of experiments are there? What kind of science has already been done? What kind of measurements have come out? Where we are headed. So I'll split in 2 sections tomorrow, and that would be the last lecture. Yes. One feed on one cylinder. You can do this for all of them.